Welcome to the Riddles and Secrets of History channel. Don't forget to subscribe so you don't miss new stories. What is the Big Bang, and did it even happen? Why does the universe not just exist, but grow? What happened in the first fractions of a second of time when there were no stars, no light, not even matter? And is it true that everything we are made of was once hot dust? Today, we will journey into the distant, almost unreachable past. Let's start with the most important thing. How did it become clear that the universe doesn't just exist, but is expanding? If you look at the night sky, it might seem like a stationary dome. Stars twinkle calmly, galaxies are frozen in their forms, and everything appears eternal and unchanging. For centuries, this is exactly what people thought, that the universe was a motionless stage where events happen locally, but space itself remains a background, like a chalkboard on which someone draws with chalk. But in the early 20th century, something happened that completely changed our view of the cosmos. It turned out that the chalkboard itself is moving, that space is not just an arena for events, but a participant in the action, that the universe is expanding. This discovery was not just unexpected, it literally turned our picture of the world upside down. And it all began rather mundanely, with measurements of light from distant galaxies. The American astronomer Vesto Slipher was the first to notice that the light from many nebulae, as galaxies were then called, was shifted to the red end of the spectrum. This meant they were moving away. He didn't yet know that he had taken the first step toward a monumental discovery. A little later, Edwin Hubble, studying the same effect in a larger number of galaxies, discovered a pattern. The farther away a galaxy is, the faster it is moving away from us. In other words, the space between us and it is growing. This discovery became known as Hubble's law. It gave the world a new understanding: the universe is not standing still. It is not static. It is growing, like the surface of a balloon being inflated with dots drawn on it. The farther apart the dots, the faster they move away from each other as the balloon inflates. This became the first indication that the universe had a beginning. If everything is flying apart now, it means that in the past, everything was closer together. You can mentally run the film in reverse. The galaxies start to come together, distances shrink, and matter becomes denser. And then comes a moment when everything we now see was contained in one tiny volume, very dense, very hot, and very distant. This idea became the basis of what we today call the Big Bang Theory. Although, of course, the word bang is more misleading than helpful. The imagination immediately conjures up an image of everything flying out from a center, like from a bomb explosion. But in the case of the universe, there is no center and no external environment into which it is exploding. There isn't even a concept of before, because time itself also begins from that point. It would be more correct to say that it wasn't an explosion, but an expansion, or even the birth of space and time. Nevertheless, the term stuck. Incidentally, it was coined not by a supporter of the theory, but by its critic, the British astronomer Fred Hoyle. He asked ironically on a radio show, "Do you really believe that everything originated from some Big Bang?" He meant it as a jab, but the term remained, and now all of science lives with it. Let's return to the observations. Hubble's law is not just a hypothesis, it is the result of direct measurements, confirmed by decades of work by telescopes and millions of spectra. Redshift is not a metaphor but a measurable effect. The farther an object is, the more its light is stretched, which means the faster it is moving away, and thus the space between us is expanding. But here too, a clarification is important. This doesn't mean that galaxies are flying through space, leaving a void behind them. No, they are, in a way, floating in space, which is itself stretching. Imagine raisins in cake dough. When the dough rises, the raisins move apart not because they are moving, but because there is more dough between them. This is how we understood that the universe is changing. It is not eternal and not constant. It lives in time. And if it is expanding, it must have had a beginning. And if it had a beginning, we can ask the question, what was it like? The answer, as is often the case in science, turned out to be complex but very beautiful. And it required not only observations but also physics. To understand what happened in the distant past, one must know how matter behaves under compression, how gas heats up, how stars are born, and, most importantly, how time and space are connected to energy and gravity. This is where the general theory of relativity enters the stage. Einstein's equations, conceived back in 1915, showed that space and time are not just a stage but active participants in the game. Mass curve space, gravity is not a force in the usual sense but a consequence of geometry, and if you set initial conditions, you can describe how the universe will change. The physicist Alexander Friedmann was one of the first to apply these equations to a model of the universe. He showed that, according to these laws, the universe must be dynamic. It is either expanding or contracting. It cannot be static, that is an unstable state. Interestingly, Einstein himself initially resisted this idea. He even introduced a special lambda term, the cosmological constant, to keep the universe static, later admitting it was his greatest blunder. But a few years later, Hubble's observations came along, and everything fell into place. The equations and observations converged. The universe is indeed expanding. This means that in the past, it was compact and dense. And everything we see today, stars, planets, galaxies, ourselves, was once compressed into a tiny volume. This is where the story of the Big Bang begins, not as a single instantaneous bang, but as a gradual expansion and cooling. A story we will break down step by step, from the first fractions of a second to the stars, galaxies, and the questions that still have no answers. But one thing can be said for sure, our universe is not static. It lives, it breathes, and everything we know is happening inside a vast, beautiful, and complex process that began 13.8 billion years ago. And it continues right now. When we hear the phrase Big Bang, our imagination conjures not only a bang but also heat, a blinding light, flames, and scorching temperatures everywhere. Intuitively, it seems that if something explodes, it must be hot. But with the universe, it wasn't that simple. In fact, the theory of an expanding universe could have worked even without high temperatures at the beginning. As late as the mid-20th century, scientists seriously discussed a model of a cold universe. Imagine space expanding, galaxies moving apart, but all of it happening in an icy silence. No flames, no heat, just expansion, like pebbles shot out in all directions in zero gravity. This hypothesis seemed reasonable until a fact emerged in the mid-20th century that changed everything. In 1965, two radio engineers, Arno Penzias and Robert Wilson, while calibrating an antenna in New Jersey, encountered a mysterious noise. It wouldn't go away, no matter where they pointed the instrument. At first, they thought birds were causing interference, then that the antenna was dirty, but no amount of effort helped. It soon became clear that this noise was coming from everywhere, from all directions in the sky with equal intensity, and it had a form characteristic of radiation that was once very hot and then cooled over billions of years. This is how the cosmic microwave background radiation was discovered, the ancient light left over from the very first moments of the universe. Its temperature today is just under 3 degrees on the Kelvin scale, almost absolute zero. But the shape of this radiation spectrum perfectly matches what we call a thermal spectrum. And this means that it once emanated from a medium with a temperature of thousands, even millions, of degrees. This is when it became clear, the universe was indeed hot at the beginning. Imagine everything we see today, stars, planets, nebulae, was once compressed into a very dense and very hot mixture. Gas, photons, elementary particles, everything was boiling in a plasma of incredible density and temperature. Over time, this mixture expanded and cooled, and after hundreds of thousands of years, it became transparent. The light that was released then is what we detect today as the cosmic microwave background radiation. But this relic radiation is not the only confirmation. There is another amazing way to check if the universe was hot at the beginning. Just look at what it was made of. In the beginning, when the temperature was high and the density was enormous, thermonuclear reactions took place. Protons and neutrons collided, fused, and light nuclei were born. It was then that hydrogen, helium, and a little lithium and deuterium, heavy hydrogen, were formed. All of this happened in the first 3 minutes of the universe's life. Such conditions have never existed since. Today, we can calculate how much of these elements should have been produced. Using the laws of physics and data on density and temperature, scientists get very precise numbers. Then they look at stars, planets, and gas clouds to check if this matches what we actually see. And yes, it matches. Not perfectly, but accurately enough to say the model works. This is especially evident in first-generation stars, which contain almost no heavy elements. They have preserved the primordial composition of matter. And this composition is exactly what should have resulted from a scorching early universe. The test was even conducted in the atmosphere of Jupiter. Its powerful gravity allowed it to preserve gases from the very beginning of the solar system's formation. A probe was sent there, which penetrated the atmosphere and measured the ratio of light to heavy hydrogen. The result confirmed it. The calculations were correct. Everything matches what the hot beginning model predicts. So, we have two independent confirmations. First, the cosmic microwave background radiation. This is ancient light that has come to us from a time when the universe was still hot and dense. Second, the composition of light elements, which can be calculated and verified. Both of these facts are observable, measurable, and verifiable. We don't just believe the universe was hot. We see it. We have measured it. We can say how hot it was and what was happening in that heat. The theory of a hot beginning is not a fantasy but a working model. It has equations, predictions, and confirmations. It says, yes, the universe is expanding. But in the past, it was compressed, dense, and scorching hot. Physical processes that we can calculate took place within it. We can even reconstruct a picture of its first minutes. However, a question remains in this beautiful scheme: where did this state itself come from? Why was it exactly like that? Why was the universe born not just hot, but also surprisingly uniform and smooth, with just the right conditions? We will begin searching for answers to these questions in the next chapter. There, we will find what is called an adventure before the beginning, a hypothesis that tries to explain why the Big Bang started exactly as it did. This is not just a sequel, but a kind of prequel. A story before the beginning of the story itself. And its name is inflation. The name Big Bang sounds dramatic. Too dramatic. It's confusing. It makes it seem as though at some moment in the void, a powerful explosion occurred, and from a single point, galaxies, stars, and planets flew off in different directions. A moment, a direction, a center, an explosion. All of this creates the wrong image. And if we truly want to understand how the universe was born, we must abandon this image. Let's start with the main point. The Big Bang was not an explosion in space, it was the expansion of space itself. It wasn't an event at a certain point. It was a state in which the entire universe existed. Not somewhere, but everywhere. When we say explosion, we imagine there was air, and suddenly, a bang, fire, a shockwave, and everything flies outward. Such an explosion has a center, boundaries, an inside, and an outside. But the Big Bang had no center and no outside. It wasn't an explosion in space, but the moment when space itself appeared. To understand this, you need to change the picture. Instead of an explosion, imagine an inflating balloon. Not the balloon itself, but its surface. Imagine you are a tiny ant living on the surface of a rubber balloon. You cannot look inside or outside. You only have access to the surface. As the balloon inflates, the distance between all the points on its surface increases. And there is no point on the balloon itself that you could call the center of the expansion. It's the same with our universe. We don't live inside the balloon or near the center. We are part of the surface, part of the space that is itself expanding. Everything around us, galaxies, quasars, dust, radiation, is not flying away from a center, but the distance between everything is increasing. Every observer in the universe is at their own center of expansion. And this is not a paradox. It's simply a feature of the geometry of a space that has no special, designated point. But if there is no center, another question arises: where did the Big Bang happen? The answer is surprisingly simple: everywhere. Where we are right now, 13.8 billion years ago, was also that same hot, dense phase. The same was true for where any other point in the universe is now. The beginning was everywhere. You could say that the Big Bang is not a place, but a moment in time. It's not an event in space, but a space-time phase, a transition from one state to another. Before it, there might not have even been time, at least not in the form we understand it. But here, another trap arises. If the universe is expanding, what is it expanding into? After all, when we inflate a balloon, it gets bigger within some external space. But the universe, what's outside of it? The answer, strange as it may sound, is nothing. The universe has no outside. Space is not expanding into something. It is simply becoming larger, as if the distances between all objects were growing, but without any edge, boundary, or external space to step into. This is difficult to imagine because our brain is accustomed to three-dimensional geometry and the experiences of everyday life. We always mentally place objects inside something larger. A ball in a room in a house in a city. But with the universe, it's different. It isn't in anything. It is everything. And if it has a shape, it's a shape without an outer shell. Astronomers even use a special term, the observable universe. This is the part from which light has had time to reach us in 13.8 billion years. Everything beyond that, we simply cannot see. Not because there's nothing there, but because information from there physically couldn't have reached us. Light simply hasn't had enough time. And this is where another important point begins. Many people ask, if we see the edge of the universe in one direction and in another, and there are 28 billion light-years between these edges, why are they the same? Why is the temperature of the cosmic microwave background radiation the same on all sides? According to calculations, these regions should never have been in contact with each other. They didn't have time. Light from one couldn't have reached the other. They are not causally connected, yet they are identical in temperature, density, and structure. This is a puzzle, and it's directly related to how we understand the Big Bang. To explain this coincidence, scientists proposed the theory of inflation. We will talk about it in the next chapter. But it's important to understand right now that the classic image of an explosion from a point leads us to many wrong conclusions. It prevents us from understanding how everything really happened. Instead of imagining an explosion, it's better to think of a phased transition of the birth of space and time, where everything began in a dense, hot, uniform state. And since then, it has just been stretching, slowly in the first moments, then rapidly, then slowly again. There was no point from which everything flew out, no void into which everything expanded. There is no edge, no center. There is only space that is growing on its own. And we are inside it. We are part of this growing world. And everything we see, everything we know, is the result of a process that began not in a place, but in time. This requires a shift in thinking, a rejection of familiar images. But this is precisely why cosmology is so valuable. It doesn't just tell us about distant galaxies. It teaches us to see the familiar in a new way. So, if you want to imagine the Big Bang, don't think of a bomb. Think of all of space at once. Imagine that everything you know was once hot, dense, and compressed, and began to expand everywhere, simultaneously, without a sound, without light, without a center. Only time, only the beginning. When we say, the universe began with the Big Bang, it sounds like a final formula. There was a moment, and from it came time, space, and events. But the deeper science looks into this beginning, the more it asks a strange, bold, but logical question: what was there before? Can we peer into what preceded the bang itself? Is it possible to find out where the perfect conditions that started it all came from? Because the more we learn, the clearer it becomes. The initial parameters of the universe are too precise, too fine-tuned, almost suspiciously so. For example, we see that the temperature of the cosmic microwave background is the same in all directions, but according to calculations, different regions could not have had time to agree with each other. Light simply didn't have time to travel between them. So why are they the same? Another example is the geometry of space. It turned out to be flat, without any overall curvature. This is a very unstable state. It requires an incredibly precise balance between the density of matter and the rate of expansion. Why did the universe start with these exact parameters? To answer these questions, a hypothesis was proposed in the 1980s that has become a crucial addition to the Big Bang theory. It was called inflation. Inflation is a special stage at the very beginning of the universe that lasted a negligible fraction of a second but changed everything. During this time, the universe expanded not just fast, but exponentially fast. That is, with each moment, its size doubled, tripled, and increased by millions and billions of times, instantly. Imagine you're inflating a balloon. Now imagine that in a billionth of a second, it grew 100 million times larger. That's exactly how, according to inflationary theory, space behaved. It swelled at a monstrous speed, literally exploding with expansion, but not in any one place. It happened everywhere at once. What caused this? According to the hypothesis, the universe at the beginning was filled with a special energy field. It's conventionally called the inflaton field. It had an unusual property: under certain conditions, instead of dissipating, it accelerated space itself. All the energy of the field went into expanding the geometry of space. As a result, space swelled like yeast dough in an oven. This state lasted for a fleeting moment, but in that short time, it managed to do the most important thing: it smoothed out the universe, made it uniform, and removed its curvature. Space became almost perfectly flat. The temperature became the same everywhere, and fluctuations were evened out. According to modern ideas, it was inflation that created the initial conditions from which the Big Bang itself later began. And then, inflation ended, not with a loud bang, but on the contrary, gently, almost imperceptibly. Scientists even came up with a special term for it: the graceful exit. It's as if the scene changed, and no one noticed how the previous one disappeared. At the moment of this transition, the energy of the inflaton field was converted into particles. Interactions, collisions, and the birth of matter began. The temperature skyrocketed. And this is where what we call the hot phase of the Big Bang begins, the one we talked about in the previous chapters. So, you could say that the Big Bang isn't the very beginning, but a consequence of inflation. Inflation itself is the prequel, the first chapter that was long unknown but was later figured out to explain the oddities of the main story. Like everything in science, the theory of inflation did not arise from nothing. Scientists from different countries worked on it. Among the pioneers were the Soviet physicist Alexei Starobinsky and later Andrei Linde, Alan Guth, and others. These ideas sounded risky and bold but turned out to be surprisingly fruitful. Inflation explained not just one, but several puzzles at once, from the geometry of space to the structure of the cosmic microwave background. Of course, the theory requires assumptions, such as the existence of that very inflaton, a still hypothetical field. But physics has long been accustomed to such assumptions. At one time, Newton's theory of gravity was also just a model that described a phenomenon without specifying the mechanism, but it worked. Inflation also works as an explanatory framework. Do we have any direct confirmation of inflation? Not yet, but scientists are looking for it. For example, the structure of the cosmic microwave background may contain imprints of gravitational waves that arose specifically during inflation. They are being searched for using special telescopes and antennas. There is also hope of catching cosmic neutrinos, particles that could carry information from those early epochs. It's not easy, but the work is ongoing. And even if inflation turns out not to be the final truth, it has already played an important role. It has shown that the Big Bang Theory has depth, that behind the beautiful picture of an expanding universe lies another layer, and perhaps more than one. So, to the question of what was before the Big Bang, science currently answers cautiously but confidently: there was likely inflation, an explosive growth that gave the universe its shape, smoothness, and initial conditions. It was this that made the birth of everything that followed possible. As for where inflation itself came from, that's the next level of questions. Perhaps we will answer it later, or perhaps it will remain beyond the limits of our knowledge, at least for a time. But we can already say that the beginning of the universe is not a single point. It's a story full of events, transitions, phases, and mysteries. And each new discovery opens the door even further toward the source, toward the first impulse or the first transition, after which everything else followed. When inflation ended and its energy was converted into particles, a completely different phase began in the universe. The temperature was enormous. Space continued to expand, but no longer at the breakneck speed of inflation, but slowly, gradually, as if after taking a deep breath, the universe began to exhale rhythmically. Everything was flooded with light, but not the kind of light we know. It was a light without photons, because photons, electrons, quarks, neutrinos, everything existed, but in the form of energy, in the form of fields. Particles were just beginning to manifest. This era didn't last long, millionths and billionths of a second. But in it, everything happened that would later make our existence possible. This is when what physicists call the Great Thermal Cookery began. The first fractions of a second were a time of a superdense plasma. There were no atoms in it, not even protons and neutrons. Everything consisted of elementary building blocks, quarks and the gluons that bound them together. It was something like a soup where all particles moved freely, collided, were born, disappeared, and transformed into one another. Constant motion, full of energy and chaos. But this chaos was not meaningless. It obeyed strict laws. As the universe expanded and cooled, the temperature dropped, and this bubbling quark gluon plasma gradually set. After about a millionth of a second, protons and neutrons began to form. Quarks could no longer float freely, they were confined inside nuclear particles. From that moment on, the universe became recognizably material. But what happened next was no less of a miracle. Protons and neutrons began to combine. In the first few minutes after the Big Bang, the temperature and density still allowed them to collide and form nuclei. This was the era that physicists call nucleosynthesis, the birth of atomic nuclei. And here's what's amazing, we can calculate these reactions. We know how protons and neutrons combine to form deuterium, heavy hydrogen, how other particles join it to form helium. We even know how much should have been produced. These calculations are not based on guesswork, but on formulas verified in nuclear physics. It turns out that we can look into the first 3 minutes of the universe through mathematics. And what we see matches what we observe in the present. Today, in stars and gas clouds, we can measure the amounts of helium, hydrogen, lithium, and other light elements, and their ratios match almost exactly what should have been produced in the hot, young cosmos. This means that our world was literally cooked in the first minutes of its life. It's astonishing. We, almost 14 billion years later, can say with confidence what was happening in a moment when the temperature was billions of degrees and time was counted in milliseconds. True, there is one discrepancy here. Everything is explained well, except for one element, lithium-7. Its predicted amount is slightly higher than what we see in stars. This discrepancy remains a puzzle for now. Maybe we don't understand something about stellar evolution? Maybe there is a missing element in physics, or perhaps it's just an error in measurement. But for now, this is one of the rare places where observations do not match the calculations. Nevertheless, the picture is clear. After the first 3 minutes, the universe had a very simple chemical composition. Almost its entire volume consisted of hydrogen. In second place was helium, everything else was just traces. There was no carbon, no oxygen, no iron. There were no rocks, no water, no life, only light elements and incredible heat. But, strange as it may seem, for a while, everything stopped. The expansion continued, but no new nuclei were being born. It had become too cold for synthesis. All that remained were individual nuclei, free electrons, and a stream of photons. There were no atoms yet. To get an atom, an electron needs to stick to a nucleus. But because of the high temperature, photons would immediately knock it back out. Therefore, matter continued to exist as a dense, hot, opaque plasma. Light could not move freely within it. The universe was filled with light that couldn't go anywhere. It was a time of waiting. Matter and radiation were seemingly frozen in a balance. This state lasted for about 380,000 years. Only then, when the temperature dropped to the right level, could electrons finally combine with nuclei, and atoms appeared. This moment is called recombination. And it was then that the universe became transparent for the first time. Nothing hindered the light anymore. It began its free journey. And this ancient light is still traveling through the cosmos. We see it today as the cosmic microwave background radiation. But more on that in the next chapter. For now, it's important to understand that the entire material universe began to form in the very first seconds. First particles, then protons and neutrons, then nuclei, then a waiting period, and then the first light that could break through matter. And all of this is not an abstract theory. These are events whose traces we can see, measure, and even reproduce in laboratories. particle accelerators, like the Large Hadron Collider, allow us to recreate the conditions of the early universe, albeit for fractions of a second. We collide protons, get new particles, observe transformations, and see how the world was born. This means that the history of matter is not a secret, but a readable text. And in this story, we are not outside observers. We are its continuation. When the light set off on its journey, the universe had already been born. It was expanding and cooling. It contained protons, neutrons, nuclei, electrons, and photons, everything needed for a complex world. But there was no light in the usual sense yet. It existed, but it couldn't move. This might seem strange. How so? There's light, but it doesn't shine. In reality, it all comes down to the state of matter. At that time, space was opaque. The universe resembled a foggy room filled with steam, where you couldn't even see your own outstretched hand. In such an environment, light constantly collides with particles and doesn't travel far. This was the early universe. The temperature was still too high for electrons to be held by nuclei. They were constantly knocked out by photons, and without electrons attached to nuclei, there can be no neutral atoms, and thus, no transparent medium. The light born in this dense plasma couldn't travel even a centimeter. It constantly collided with electrons, scattered, and lost its direction. It was a dense light broth where photons and matter existed as a single, inseparable whole. This phase lasted for a long time, about 380,000 years. During this time, the universe expanded hundreds of times. The temperature dropped, and the density decreased. Finally, a moment came when everything changed. At a temperature of about 3000 Kelvin, electrons were finally able to settle into orbits around nuclei. Neutral atoms appeared, first hydrogen, then helium, and with them came the ability for light to move freely. This was the moment of recombination. It can be compared to how fog dissipates after rain. Suddenly, you can see, light travels in a straight line, and the world becomes transparent. Physicists call this transition the decoupling of matter and radiation. Before this moment, they were as one. Afterward, they went their separate ways. Matter began to gather into structures, and light began its free journey across the universe. And this light, which set off on its path 13.8 billion years ago, is still traveling. It fills all of space. It doesn't carry images like light from the sun, but it carries information about that time. This is the cosmic microwave background, CMB, radiation, the ancient light that we detect today with radio telescopes. It's important to understand that this light does not come from any particular object. It's not a star's flare-up. It was space itself that was glowing when it became transparent. And now, billions of years later, we can measure this light with incredible precision. A map of the CMB is like a photograph of the infant universe. It shows what it was like 380,000 years after its birth. And this map doesn't show chaos, but a subtle structure, tiny temperature deviations, slightly denser and less dense regions, the seeds of future galaxies. Yes, it was these small, random, quantum, elusive fluctuations that became the beginning of what would later turn into stars, planets, and us. Without these spots, there would be no structure. The universe would have remained a uniform gas, beautiful, but empty. The study of the CMB has become one of the greatest achievements of 20th and 21st century astrophysics. It was measured by missions like COBE, WMAP, and Planck. They gave us a map of the universe with an accuracy of millionths of a degree. That's like measuring the temperature of the entire Earth and noticing a 1-degree difference between Antarctica and the tropics. And this data isn't just beautiful, it confirms everything the theories predicted. It shows that the universe was indeed expanding, that it had a hot beginning, that it's flat but not perfectly uniform, and that the fluctuations, those very seeds, truly existed and are of the exact scale predicted by the theory of inflation. Thus, the CMB became the oldest evidence of the universe's birth. It is older than all the stars, all the planets, and all the atoms we are made of. It is not just light, it is time, flying toward us through space. And it says, yes, there was a beginning, there was heat, there was expansion. There was darkness, and then there was light. However, to say that the universe lit up then wouldn't be entirely accurate. It simply became transparent. Light didn't begin to be born, it was simply set free. And this ancient light is still with us. It's cold. Its temperature is just under 3 degrees above absolute zero. It's not visible to the naked eye, but it's everywhere, in every direction. It permeates everything like an echo of an ancient event. And this echo does not fade. It reminds us, we live in a world that had a beginning. And we can see that beginning. Next, a new story begins, the story of structure. Matter will gather into clumps, clumps into clouds, and clouds into galaxies. But all of this only became possible because darkness gave way to light. It is from this moment that the cosmic landscape we know begins. And the first chapter of its topography is darkness and ancient light, frozen in equilibrium. When the universe became transparent, light began its journey, and space filled with an ancient glow. But this light was not the only thing that shaped its future. At the same time, acting in the shadow of the light, was another, far less understood player. Without it, there would be no galaxies, no stars, no us. Its name is dark matter. The paradox is that dark matter doesn't shine. It doesn't emit, reflect, or absorb light. We can't see it, but it affects everything we can see. And this influence is impossible to miss. To understand how we learned of the existence of dark matter, we must again turn to the motion of galaxies. If you look at a spiral galaxy, you can measure how fast its stars are rotating. And here's where things get strange. The stars on the periphery are rotating too fast, as if they are being pulled by something powerful, far more powerful than the visible mass. The same thing happens in galaxy clusters. The gravity from the visible matter, stars, gas, dust, cannot explain why they don't fly apart. Something is holding them together, something heavy but invisible. And this something was named dark matter. According to calculations, there is 5 times more dark matter in the universe than ordinary matter. That is, the lion's share of all matter is dark matter. It turns out we live in a thin layer of visible matter, surrounded by an ocean of something that doesn't shine but has gravity. In the early stages of the universe's history, the role of dark matter was particularly crucial. After recombination, when light was set free, ordinary matter, hydrogen and helium atoms, began to fall into gravitational wells. But where did these wells come from? The answer: from dark matter. It doesn't interact with light, so it didn't get stuck to photons. It had already begun gathering into clumps long before. And these clumps became the very gravitational centers into which gas clouds later flowed, forming stars. Without dark matter, the universe would have remained too smooth, too uniform. There isn't enough ordinary matter to form structures in such a short time. But with dark matter, everything worked out. It created the scaffolding upon which our entire familiar universe was later built. You can compare it to sculpting. Dark matter is like the wire skeleton inside a sculpture. Without it, the clay would collapse. It provides the shape, even if it's not visible. But what is this substance? This is where the real mystery begins. We don't know. It's not electrons, not protons, not neutrons. It's not atoms, molecules, dust, or gas. It's not just something far away. It is a fundamentally different form of matter. Scientists speculate that dark matter consists of unknown elementary particles that interact weakly or not at all with ordinary matter. These hypothetical particles have been given various names: WIMPs, weakly interacting massive particles; axions, sterile neutrinos. No one has caught them yet, but everyone is looking. Detectors are set up in underground laboratories around the world, filled with noble gases, ultra-sensitive sensors, and crystals cooled to absolute zero. Scientists are waiting for at least one dark matter particle to eventually collide with the nucleus of ordinary matter and produce a signal. One spike, one flash, and it will be the beginning of new physics. But for now, there is silence, no direct traces, only indirect evidence: gravity, mass distribution, the effect of gravitational lensing, and the motion of galaxies. And yet, the role of dark matter in the history of the universe is fundamental. It was thanks to it that the structure of the cosmos appeared so quickly. It created the seeds for future galaxies. It was the first architect of the universe. And we are the descendants of that architecture. Interestingly, dark matter is not distributed uniformly. It forms a huge halo around galaxies. We live inside such a halo. Right now, streams of dark matter particles are passing through our bodies, our homes, our planet. We are like fish swimming in an invisible ocean, and we don't even feel it. Some scientists suggest that dark matter may be connected to a deeper structure of reality, to extra dimensions, to symmetries that are still hidden. Perhaps it is the key to unifying gravity and quantum mechanics, or maybe it's just a special form of matter that was born in the early universe and has peacefully coexisted with us ever since. Paradoxically, for light to be born, darkness was needed. Without dark matter, structures could not have formed. Without it, there would be no gravitational wells. There would be no galaxies, no stars, no life. Thus, the universe reminds us once again, sometimes the invisible is more important than the visible. Sometimes, the most important thing is not what catches the eye, but what acts silently, imperceptibly, from within. And so, before we talk about the stars, we should thank the darkness. It gave them a chance to be born. After recombination, when the universe became transparent, a long pause followed. Light was set free. Atoms of hydrogen and helium filled space. Everything was quiet, uniform, and cold. Darkness without candles. This period is called the Cosmic Dark Ages. It was a time when there were no stars yet, but everything was ready for them. Gravity was slowly pulling matter into dense patches, and crucially, dark matter had already formed the scaffolding for future galaxies. But for now, everything remained in shadow. Several 100 million years passed. Perhaps 200, maybe 300, it's hard to say for sure. But one day, somewhere in the universe, the first light began. It was the moment the first star was born. These stars were unlike the ones we are familiar with. They are called population 3 stars, hypothetical, the most ancient. They were composed almost entirely of hydrogen and helium. They had no heavy elements, carbon, oxygen, iron, because those elements simply didn't exist yet. They were gigantic, bright, hot stars, possibly hundreds of times more massive than the Sun. They lived short lives, just a few million years, and then exploded as supernovae, spewing the first heavy elements into space, the very stuff that would later become part of planets, soil, breath, and us. It was inside these stars that chemical evolution began. What would later form rocks, water, and bodies was forged in the cores of the first stars. These processes are called second-generation nucleosynthesis, no longer just primordial hydrogen and helium, but carbon, oxygen, nitrogen, and metals. Everything that makes matter diverse. When such stars exploded, they not only ejected elements, they triggered a chain reaction. The shockwaves compressed the surrounding gas, causing the birth of new stars. Thus began the first stellar nurseries. Over time, individual stars gathered into galaxies, huge islands of matter and light. They were drawn to the gravitational centers made of dark matter. They collided, merged, and grew. Galactic evolution began, a process that continues to this day. During this period, another important event occurred: reionization. Remember how during recombination, electrons combined with nuclei to form neutral atoms? Well, the radiation from the new stars, especially ultraviolet light, was so powerful that it began to rip those atoms apart again. The atoms were reionized, but this time by the light of new stars. This didn't ruin the transparency of the universe, on the contrary, it made it definitively clear. The previously uniform hydrogen was now ionized, making it easy for light to pass through. The universe became truly bright. The first galaxies were small, but gradually, by merging with each other, they grew larger. Some of them became similar to the Milky Way. Our ancestors, not only biological but also galactic, were formed during this time. Between these galaxies, the cosmic web began to form, a network of dark matter and gas connected by filaments. It is a vast structure that spans the entire universe. It resembles myriads of dots connected by thin lines, like the nervous system of the cosmos. We can see this web today in large sky surveys. It is a direct continuation of the fluctuations that appeared in the cosmic microwave background. The process of galaxy formation was not instantaneous. It lasted for hundreds of millions of years. And it's not over yet. New stars are still being born today. New collisions happen in space every second. The universe is alive, it hasn't frozen, it's working. And all of this began from the moment when gravity overcame dispersion, when clumps began to gather, when the conditions for the first flare-up appeared. Then the first light was born, not just from plasma, but from stars. This light did not reach us directly. It was absorbed, scattered, and distorted. But we see its consequences. We see galaxies scattered across the sky. We see the chemical composition of matter. We see the structure of the universe. We see what can only be born inside gravitational cradles. And even more, we see ourselves. Because every atom of oxygen we breathe, every atom of calcium in our bones, the iron in our blood, all of it was once inside a star. And that star, perhaps, was born in one of the first galaxies, or in their descendants, or in the descendants of their descendants. So, when we look at the sky, we see not only light but also history. And in this history, the first star is not just a flash. It is the first line of a song that continues to this day. It would seem that by this point, we have everything: matter, light, stars, galaxies, dark matter. The universe is working, it's growing, developing, creating structures. But at the turn of the 21st century, it turned out that this picture has another layer, the strangest, most unexpected, and most dominant of all. It was named dark energy. How did we find out it exists? It all started with observations of supernovae. Astronomers noticed that distant Type Ia supernovae, a special kind of stellar explosion, appeared dimmer than they should have. This meant they were farther away than expected, which in turn meant that the expansion of the universe is accelerating. But that's absurd. Gravity should be slowing down the expansion, as all matter pulls on itself. Even with dark matter, the expansion should either be slowing down or stopping. But it's not just not slowing down, it's speeding up. It's as if someone, invisible and powerful, is pulling space outward, stretching it faster and faster. This led to the idea of dark energy, some form of energy that fills all of space and has a special property: it repels rather than attracts. It's not a force in the usual sense. It's not a field, not particles. It's a property of space itself. Interestingly, Einstein once proposed something similar. He introduced a special term into his equations of general relativity, the cosmological constant, lambda term, to allow for a static universe. He later called it his greatest blunder, but perhaps it wasn't a blunder at all, but a premonition. Today, the lambda term has returned to science. The modern cosmological model is called the lambda-CDM model, where lambda is dark energy, and CDM stands for cold dark matter. This model is the working basis of all modern cosmology. So what is dark energy? Honestly, we don't know. It has no mass. It cannot be seen. It doesn't interact with matter, but it exists, and its influence can be measured. It makes up approximately 70% of all the energy in the universe. 70%. The rest is dark matter and ordinary matter. Essentially, everything we know makes up less than 5%. All the rest is either dark or incomprehensible. This is astonishing and a little unsettling. We live in a world where the vast majority is invisible, misunderstood, but determines the future. Dark energy is anti-gravity. It doesn't push objects apart or destroy galaxies. It simply stretches the space between them. Gradually, imperceptibly, but relentlessly. The larger the universe becomes, the more dark energy there is in it. Because it doesn't get diluted, its density remains constant for every cubic meter, and the number of such meters is increasing. This means that over time, dark energy will become increasingly dominant. It already is. Gravity is no longer capable of holding back the overall acceleration. Space is speeding up, and this is not a temporary effect. It's a trend. Where does this lead? There are several scenarios. Eternal acceleration, the big freeze/heat death. The universe will expand faster and faster. Galaxies will move farther and farther apart. One day, the light from them will no longer reach us. The night sky will go dark. Everything except the closest stars will disappear beyond the cosmic event horizon. The cosmos will become dark, cold, and empty. The Big Rip: if dark energy is not constant but increases in strength, then in the distant future, it could start to tear apart not only galaxies but also stars, planets, and even atoms. Space will expand so rapidly that it will destroy everything down to the elementary particles. The end in absolute disintegration. There are also more optimistic hypotheses. For example, that dark energy is a temporary effect related to a vacuum phase transition, or that it's a manifestation of something deeper, an extra dimension, a quantum field, the residual pressure from inflation. But these are all just theories for now. Today, we observe. We measure redshifts, the structure of galaxies, and the fluctuations in the CMB. We build maps of the cosmos to understand how dark energy affects the growth of the universe. But for now, it's as if we can feel its presence without knowing what it is. This is reminiscent of the early centuries of physics when people knew electricity existed but didn't understand what it was. They built models, observed effects, and searched for patterns. So do we. We see the acceleration, we see its influence, but we don't know why. Perhaps dark energy is not a mistake of nature, but its profound property. Maybe space is inherently unstable. Maybe it lives, pulsates, moves. And we are just observing another phase of its life. In any case, we now know that the expansion of the universe will not stop. It's not just continuing, it's accelerating. And this is the main paradox of modern cosmology. Everything was born from a dense, hot point, then expanded, then should have slowed down, but instead, it is speeding up. It's as if after a long inhalation, the universe remembered it could breathe more deeply and began to grow, infinitely, coldly, and at an accelerating rate. What happens next, we don't know, but we know for sure light, matter, and stars are only part of the story. The rest is the dark side of the cosmos. Without it, none of the calculations add up. It seems we have traveled the entire path, from a moment when even time did not exist to billions of stars, galaxies, planets, dark matter, and accelerating expansion. We see how it all began, how it progressed, and how it continues. But inevitably, the question arises, how will it all end? This is not just a philosophical interest. It's a question of physics, of laws, of trends. Because if the universe had a beginning, could it also have an end? There are several scenarios, and each depends on key parameters: how much matter is in the universe, how it is expanding, and how dark energy behaves. The Big Freeze, heat death. This is the path of eternal expansion. It assumes that dark energy is constant and gravity is no longer sufficient to slow down the growth. In this case, galaxies will move farther and farther apart. The light from them will one day cease to reach us. The sky will become empty. The stars will burn out, leaving behind white dwarfs, neutron stars, and black holes. Then even they will decay. The universe will become dark, cold, and lonely. It's not a catastrophe, not an explosion, just a slow fading away. The Big Rip. This is possible if dark energy is not constant but is strengthening. Then, at some point, it will begin to stretch not only galaxies but also stars, planets, and even molecules. Everything will crumble as space itself is torn apart. This is an end by flying apart, absolute disintegration. The Big Crunch. This option suggests that the expansion will one day stop, and the universe will begin to contract. Everything that is now moving away will turn back. The future will be a reverse journey. Galaxies will approach each other, density will increase, temperature will rise, and once again, a singularity. A second Big Bang, or an end forever, we don't know. For now, all data points to the first scenario, eternal, accelerating expansion. But we cannot look too far ahead. Perhaps the laws will change. Perhaps dark energy is unstable. Perhaps new discoveries are on the horizon. Interestingly, there is another option, the multiverse. The theory of inflation we discussed earlier allows for our universe to be just one bubble in an infinite sea of others. In each of them, there are different physical laws, different initial conditions. We live in this one because it allowed for the existence of matter, stars, and observers. The others could be completely different. If this is the case, the end of our universe may not be the end of everything, but just one episode in an infinite book. And now, a question that cannot be avoided. If the universe will one day disappear, is there any meaning in what we do in it? This is not a scientific question, it's a human one, but there is an answer to it as well. Understanding the structure of the universe is part of what makes us thinking beings. We are not just matter that appeared by chance. We are matter that has become aware, that can describe its history, ask questions, build a telescope, look at the cosmic microwave background, measure redshift, and understand inflation. We are the part of the universe that can speak on its behalf. And in a sense, as long as we think about the universe, it continues to live within us.